Hello everyone and welcome back to another calculus video. In this video we are going to explore the idea of power series, a series that's in the form the sum equals from 0 to infinity of c sub n x to the n is equal to c naught plus c1x plus c2x squared, and then so on. So this is called a power series. Notice that when I expand that summation, it's creating, you can think about it like an infinite polynomial. We would say this power series is centered at 0, 0. Now, if we change this and do a transformation, instead of being centered at 0, if I want to center it at x equals a, I can replace that x with x minus a to force it to be centered somewhere else. So this is the sum from n equals 0 to infinity of c sub n x minus a to the n. So if I plug in 0, I'm going to get c naught. If I plug in 1, I'm going to get c sub 1 times x minus a to the first. If I plug in 2, I'm going to get c sub 2 times x minus a squared, and so on. So again, it's an infinite polynomial. It's just centered at a different place. Let's talk about the convergence of a power series. Let's consider a generic power series, the sum from n equals 0 to infinity of c sub n x minus a to the n. The series is going to satisfy exactly one property. Either the series is going to converge at x equals a, so that's where it's centered, and diverge everywhere else, or the series is going to converge for all real numbers, or there's going to be some interval where the power series would converge. So then the question becomes, how can I figure out where a power series is going to converge? We're going to use the ratio test to help us determine where this converges. So remember the ratio test, we're looking at the sum from n equals 1 to a of a sub n. We would take the limit as n goes to infinity, the absolute value of a sub n plus 1 over a sub n. And if that limit is less than 1, then we would say that series converges. So graphically, if we were to think about that interval convergence, there's one of three things that's going to happen. It's either going to converge at the places centered, it's going to converge everywhere, or it's going to converge on some kind of interval where that value that where we're centered, I'll call it a, lives between a plus r, which is the upper bound, and a minus r, which is the lower bound, and that r is the radius of convergence. And that r is the distance from the center out to the bound. So this would be r, and this guy would be r. So let's look at a few examples where we want to find the interval of convergence. So the first one, we're looking at the sum from n equals 0 to infinity of x to the n over n factorial. We're going to use that ratio test. So we're going to take the limit as n goes to infinity of a sub n minus 1, or sorry, n plus 1 over a sub n. So if I plug in n plus 1, I'm going to have x to the n plus 1 over n plus 1 factorial. And then I'm going to divide that by a sub n, which is x to the n over n factorial. And I'm writing it this way with that traditional divide by sign when we know, because we know we're going to have to do keep, change, flip. Keep the first fraction, change the division to multiplication, and flip the second one. And then now we're going to be able to do some fancy math. So we're going to take the limit as n goes to infinity This is x. If I think about how I can reduce those x's, when we divide and we have the same base, we would subtract the exponents. So n plus 1 minus n is going to leave me an x to the first. And then we're going to have an n factorial in the numerator. That n plus 1 factorial could be rewritten as n plus 1 times n factorial. And now we can see those n factorials cancel. So we're going to take the limit as n goes to infinity of x over n plus 1. And remember, I'm taking the limit as n goes to infinity, so x isn't really being affected. So I could pull the absolute value of x out, take the limit as n goes to infinity of 1 over n plus 1. Now, I don't need the absolute value on that because 1, I'm heading to infinity, and 2, remember, n started at 0. So n's going to be positive numbers anyway. So this is already going to be positive. This guy, the limit as n goes to infinity of 1 over n plus 1, is heading to 0. And 0 times anything is 0. And that is always less than 1. So what we can see here is that this guy is going to converge for all x values. So the interval convergence is from negative infinity to infinity, and the radius of convergence radius convergence is infinite because the distance from the center, and this thing would be centered at 0, because I could think about my x minus a to the n there, and a would be 0 in this case. The distance from 0 to infinity or negative infinity is going to be an infinite distance. That's part A. B is a little bit different. We're looking at the sum from n equals 0 to infinity of n factorial times x to the n. So we're going to apply that test, that ratio test, looking at the limit as n goes to infinity. So this is n plus 1 factorial x to the n, and we're going to divide by n factorial x to the n. Don't forget the absolute value. Clean up my notation here. So now I'm going to do a rewrite. Oops, I forgot the n plus 1. So it's a sub n plus 1 over a sub n. So I can rewrite n plus 1 factorial as n plus 1 times n factorial. I can see the x's are going to reduce. X to the n plus 1 over x to the n is just x. And then again, I'm going to see that n factorial cancel. I've already reduced the x's in this notation. So I've got that absolute value of x that I can pull out. Limit as n goes to infinity. Absolute value of n plus 1. I really don't need the absolute value there because this is always going to be positive, again, because n starting at 0 and going to infinity. So I could just write it with parentheses. And clean up my infinity sign, and this guy is heading towards infinity. And what that means is that this is never going to be less than 1. So it's never less than 1. So the series is going to diverge for all x values. We're trying to figure out the limit on x where this sequence is going to converge in all three of these. So it diverges for any x value I plug in, except when x is at its center, which is 0. So the interval convergence in this case is just the single value x equals 0. And the radius of convergence, we would say, is 0. Because there's no distance between where it's converging and that outside bound. Because it's converging only at that single point. So then let's look at C. We're looking at the sum from n equals 0 to infinity of x minus 2 raised to the nth over n plus 1 times 3 to the n. So we're going to use that ratio test again, taking the limit as n goes to infinity, absolute value. So it's going to be, we're going to plug in n plus 1 for all the n's. If I do n plus 1 there, I'm going to get n plus 2. I'm going to do, since that's a fraction, I'm going to write the traditional divide by sign. So we can write our keep change flip. That's a sub n. So I've got a sub n plus 1 divided by a sub n. Take the limit, and then it goes to infinity. Now I'm going to do my keep change flip. So inside absolute value, we have x minus 2 raised to the n plus 1 all over the quantity n plus 2 times 3 to the n plus 1. And then now it's times n plus 1 times 3 to the n all over x minus 2 raised to the n. So let's see if we can simplify this a little bit. So I can see those x minus 2's are going to reduce. So I'm going to have an x minus 2 left. I can see the 3's are going to reduce. So I'm going to have a 3 left in the bottom. And then the n plus 1 is still in the numerator, and the n plus 2 is still in the denominator. So I have the limit as n goes to infinity of the absolute value of x minus 2 times n plus 1 over n plus 2 times 3. So I'm going to pull out the absolute value of x minus 2, and then the absolute value of 3 is just 3. And that's going to leave me with the limit as n goes to infinity of n plus 1 over n plus 2. We know this limit is going to head to 1. We can use L'Hopital's to show that. That's going to be infinity over infinity. So if I reevaluate that limit, take the derivative of the top and bottom, the derivative of each is 1, so that limit's going to go to 1. So there's some side work for that. So this is going to be equal to absolute value of x minus 2 over 3 times that limit value, which is 1. So that's what our ratio test is going to give us. We get x minus 2 over 3. Now, because we're using the ratio test, we know this thing is going to converge if the absolute value of x minus 2 over 3 is less than 1. So to figure out the interval of convergence, we want to get x by itself. So I'm going to multiply both sides by 3. So absolute value of x minus 2 is less than 3. I can rewrite that as negative 3 is less than x minus 2 is less than 3. And then we've got this inequality to solve. We're going to add 2 everywhere, middle and outsides. So I'm going to get negative 1 is less than x is less than 5. So our interval of convergence for this one is from, well, we know it's negative 1 to 5, but now we really need to test the endpoints. So I need to insert a new page so I have more room. So we know everything between negative 1 and 5 is going to force convergence, but we really don't know anything about the endpoints, so we have to test those endpoints separately. So what does that mean? That means we're going to plug in -1 and then we're going to plug in 5 into that series. And that series was the sum from n equals 0 to infinity of x minus 2 to the n over n plus 1 times 3 to the n. So I'm going to rewrite that series over here. Series n equals 0 to infinity. X minus 2 to the n over n plus 1 times 3 to the n. So when I plug in -1, I'm going to get the sum of -1 minus 2 to the n over n plus 1 times 3 to the n. I'm going to simplify this. This is -3 to the n over n plus 1 times 3 to the n. I could think about -3 as -1 times 3 raised to the nth over n plus 1 times 3 to the n. And then I can write this -1 times 3 as -1 to the n times 3 to the n over n plus 1 times 3 to the n. And we're going to see those 3 to the n's cancel. So we're going to be left with the alternating series, -1 to the n over n plus 1. We want to know what's happening with this. Does this converge or does it diverge? This is an alternating series. So we can use the alternating series test to determine convergence or divergence. So we have to check two criteria with the alternating series. The first one is it decreasing? And we're looking at the non-alternating part. For us, this would be 1 over n plus 1. So is the sequence decreasing? So not negative. 1 over n plus 1 plus 1. Is that next term smaller than the previous term? And I have 1 over n plus 2, and that is less than 1 over n plus 1. So it is decreasing. And the second thing, does the limit of the sequence 1 over n plus 1 go to 0? And it does. So we can say, therefore, this guy is converging by the alternating series test. I'll abbreviate that AST. So it does converge at the endpoint, x equals -1. But now we got to test the other one. So we've got to test x equals, was it 5? Yep, 5. So we're going to plug 5 in for x into this sequence, and we want to know what's happening to that. So we're going to have the sum from n equals 0 to infinity, 5 minus 2, to the n over n plus 1 to the 3n. 5 minus 2 is 3, so I have 3 to the n in the numerator over 1 n plus 1 times 3 to the n in the denominator. So I have 1 over n plus 1. I want to know what's happening with that. So we could think about a couple of different things. We could use a couple of different tests here. We could do a comparison to 1 over n, which is the harmonic series, or we could use the integral test. So I think I'm going to use the integral test. So the integral test says that sequence has to be positive, decreasing, and continuous, and it is. So I'm thinking about comparing it to the function 1 over x plus 1. So I would integrate from 0 to infinity of 1 over x plus 1, which is positive, decreasing, and continuous on some interval. In this case, I'm looking at the interval from 0 to infinity. I would rewrite this as the limit as b goes to infinity of 0 to b of 1 over x plus 1. And when I integrate that, I'm going to get the ln. So this is going to be the ln of x plus 1 going from 0 to infinity. And let me clean up my notation. That says limit, but there, I'll print it. So we have the limit as b goes to infinity. Fundamental theorem of calculus is next. Ln absolute value of b plus 1 minus the ln absolute value 0 plus 1, which is 0. Ln of 1 is 0, so that's going to go away. As b gets bigger and bigger, that limit is getting larger and larger, so the integral diverges, which means that the series diverges also. Okay, which means we cannot include that endpoint. So my interval of convergence went from -1 to 5. We cannot include the 5. We can include the -1 because when I plug in the -1, I do get a series that converges. Every number in between -1 and 5, and there's an infinite number of numbers between there, would also force convergence. Now, this thing was centered at x equals 2. If we compare our original series to that x minus a that would be here, we can see it's centered at 2. So if I'm looking at the interval from -1 to 5 and I'm centered at 2, that radius of convergence is the distance to the outside, to that upper bound and that lower bound. So the radius of convergence is going to be equal to 3 in this case, 5 minus 2, or we could think about 2 minus -1. So let's write out the steps here. Steps for finding the interval of convergence. We've seen all three cases in these three examples. So you're going to apply the ratio test. Okay, if you get a finite number, then we know that that value to force convergence has got to be less than 1. Whatever you get when you apply that ratio test has to be less than 1. So then that gives you an inequality to solve. And then after you solve that inequality, you have to test each endpoint. Okay, that's exactly what we had it in example 3. Now in example 2, things were a little bit different, and same thing with example 1, that second step was different. Because when we found that limit, this was example 3, when we found that limit, as in went to infinity, we ended up with something here that had to be less than 1. That didn't happen in example 2. In example 2, when we found that limit, it was infinite, which meant that this is always going to diverge. So there's nothing really more to do there if it's always diverging, except when x is at its center, then the interval of convergence is that single point, and the radius of convergence is 0 because it's just one single point. But in example A, that first example, that limit went to 0, and 0 times anything gives us 0, and 0 is always less than 1, which meant it converged everywhere. So it really depends on what happens with that limit as to whether or not you have to test endpoints, because in case 1 and 2 we did not, but case 3 is where we had to test endpoints. So I put a little asterisk beside that step just to keep that in mind. So let's look at another example. In example 2, they want us to sketch the graph of f of x equals 1 over 1 minus x, and then find the graphs of the corresponding partial sums. S of n of x equals the sum from n equals 0 to capital N of x to the n for capital N equals 2, 4, and 6 on the interval from -1 and 1. So we're going to see that this polynomial is going to approximate this graph of that rational function. And the more partial terms that we have, the better that estimate's going to be. And it's going to really hug that rational function, especially on that small interval from -1 to 1. So this series is centered at 0. If we think about that x minus a to the n here, we could think about x to the n as x minus 0 to the n. So we're going to graph the function 1 over 1 minus x, but let's first find some partial sums. So we're going to find s of 2, s of 4, and then s of 6. So if we plug in 2, well, we'll start with 0. If I plug in 0, I'm going to get x to the 0 plus x to the first plus x to the second. So this is going to be 1 plus x squared. So that's a quadratic. If we want S4, that's the first 4 sums of first 4 terms for the partial sum. So x to the 0 plus x to the first plus x to the second plus x to the third. That would be 4. S to the S. Hold on. I'm starting at 0. N equals 1, n equals 2, n equals 3, n equals 4. This was n equals 0 and 1 and 2. So S4 is going to be 1 plus x squared plus x cubed. S6 is going to be x to the 0, which is n equals 0, x to the first plus x squared plus x cubed, n equals 4 is going to give us x to the 4th, n equals 5 is going to give us x to the 5th, and n equals 6 is going to give us x to the 6th. I need to go back and fix that partial sum for 4 because I skipped a number. N equals 0, and n equals 1, n equals 2, n equals 3, and then n equals 4 would be x to the 4th. There we go. So now let's graph all this in Desmos. So here's my graph, 1 over 1 minus x. It has a vertical asymptote at 1. When I graph that first partial sum, 1 plus x squared, and remember, we only cared about what happens between -1 and 1. You see how around 0, that curve really lays on top of that red graph? The red graph's the original rational function, but it's hugging it. Now, if we use a few more terms, that S4, the fourth partial sum, that green curve is an even better model for that red one, that original function. And then if I use more terms, it's an even better model. Let me just take those other ones off. So what we're doing, and what we'll see later when we talk about Taylor and Maclaurin series, is that we could take some of these functions that are not nice, like 1 over 1 minus x, and if we really only care about a certain interval, in this case from -1 to 1, then maybe we can use enough terms to model it as a polynomial so that it produces a really good fit. Why would we care about using the polynomial? because polynomials are really nice to deal with, especially when you have to do complex math with them. So that's where we're heading later in this section. But right now, I just want you to see that if we have this function, they did give us that series to use. And if we use partial sums, we can model that thing nicely. The more terms we use, the better that fit's going to be. So let's look at the next example. We want to use a power series to represent each of the following functions, and then we're going to find the interval of convergence for them. So you guys remember back when we talked about geometric series? We said we could write it as the sum from n equals 1 to infinity of ar to the n, or we could start it at 0. Oh, sorry, ar to the n minus 1. Or we could start it at 0 and it's ar to the n. And if it converges, then the sum is equal to a over 1 minus r. So what we're going to try to do is force this 1 over 1 plus x cubed in a to look like this a over 1 minus r. And if I can do that, then I can look at creating that geometric series. So let's look at that. We've got 1 over 1 plus x cubed. I could think about that as 1 over 1 minus negative x cubed. So then my a is 1 and my r would be negative x cubed. So I could write that sum from n equals 0 to infinity, and we do want these to start at 0, of ar to the n as a, which is 1 times negative x cubed to the n. And this is going to converge as long as that radius is less than 1. As long as the absolute value of r is less than 1, not the radius, the ratio there. So I'm going to clean this up just a little bit. So this is the sum from n equals 0 to infinity of negative x cubed to the n. So this is a geometric series, and we know geometric series will converge if the absolute value of r is less than 1. So this thing converges as long as the absolute value of negative x cubed is less than 1. So that means negative x cubed has to live between negative 1 and positive 1. If I divide everything by negative, that's going to flip all of my inequalities. And then if I take the cube root of the middle and then the outsides, I'm going to get 1 is greater than x is greater than negative 1. So this thing is going to converge for negative 1, all values from negative 1 to 1. And notice I'm using parentheses there. I cannot include the endpoints because I use the idea of the geometric series to determine convergence, and it only converges when the absolute value of r is less than 1, strictly less than 1. Now, if I wanted to, I could use the ratio test and I would get the same conclusion. It's just going to take a little bit more work because we would use the ratio test, we would find that interval, and then we would have to test each endpoint, and we would see that each endpoint would diverge. So let's look at this last one. We're looking at the function x squared over 4 minus x squared. Our goal is to rewrite it as a over 1 minus r, so we could express it as a geometric series. So I really need a 1 right here where that 4 is. So let's factor a 4 out. So if I factor a 4 out, I'm going to be left with 1 minus x squared over 4. Okay, algebraically, that would give me back what I started with. And then I'm going to think about rewriting that x squared over 4 as x over 2 quantity squared. And then instead of having x squared over 4 times 1 minus the quantity x over 2 squared, I can write it as a complex fraction. So x squared over 4 divided by 1 minus x over 2 quantity squared. And now I'm in that format for that geometric series, so I can identify A and R. In this case, A is x squared over 4. R is x over 2 quantity squared. So my geometric series, and we would write this from n to infinity of a times r to the n. So this is going to be the sum from 0 to infinity. A is x squared over 4. R is x over 2 quantity squared, and that's raised to the n. Now I'm going to clean this up just a bit. So this is the sum from n equals 0 to infinity of x squared over 2 times x squared over 4 times x over 2 to the 2n, power to a power, we multiply those powers together. And we could leave it like that, or if we wanted to, we could simplify this a little bit more. So it'd be perfectly fine to leave it that way. But if we wanted to, this is x squared over 4. And we could think about this x over 2 to the 2n as x to the 2n over 2 to the 2n. So I have x to the second power times x to the 2n in the numerator, and that would be x to the 2n plus 2. And then the denominator, I have 4 times 2 to the 2 to the 4, which is 2 squared to the 2 squared to the n, which is 4 to the n. So we could rewrite this as x to the 2n plus 2 all over 4 to the n plus 1. Now let's talk about where this is going to converge. Since it's geometric and we have that r value, it's going to converge anywhere the absolute value of r is less than 1. So we need the absolute value of x over 2 quantity squared to be less than 1. And we're going to solve this inequality. So that means the absolute value of x squared over 4 is going to be less than 1. I'm going to rewrite that as x squared over 4 is wedged between -1 and +1. Multiply both sides by a 4. And then take the square root of both sides. So that means our interval convergence would be between -2 and 2. Notice we do not include the endpoints because, again, this is geometric, so that r value has to be strictly less than 1 to convergence.